Hello, and welcome to the CPM webinar series. Today's topic is an overview of strand pelletizing applications. My name is Christian Davis, and I will be your moderator for today's event. With locations around the world, CPM is a leading global supplier of twin screw extruders, extrusion systems, high performance replacement parts, ring extruders, thermal equipment, and supporting services. Our webinars are intended to service, support, and inform you about the latest technologies, maintenance methods, and trends in the industry. Presenting today's webinar is Darren Frame. Darren has over 20 years of manufacturing experience in various industries, including thermoplastics. More than a decade of his work has been directly related to extrusion compounding using co-rotating twin screw extrusion technology. At CPM, Darren works closely with our customers to support their application needs with respect to machine configuration, screw configuration, technical training, and other process improvement initiatives. If you have any questions during the webinar, please type them in the questions field. If they're not answered, you'll receive a follow-up response by email. Darren, I'll now turn it over to you.
All right, thanks, Christian, and welcome everyone to this month's webinar. We'll go through this on strand pelletizing. Outline here, we'll look at kind of the basic process flow of strand pelletizing. We'll look at some options on the material delivery and tempering from die to pelletizer. We'll touch on some points with challenges with strand dies, some of the challenges with the material exiting the strand die. We'll cover a little bit on pelletizer design, and then we'll take a look toward the end on pellet quality and some common issues. One thing about strand pelletizing is it is a kind of your more economical way of pelletizing materials off of a twin screw. It's fairly universal for most product applications where it struggles a little with your rubbery or more elastomer type grade materials. And as I mentioned, there's several options on the way the material can be conveyed from the die and tempered toward the pelletizer. Most options are fairly easily on maintenance accessibility, and it's suitable for quick changeover cleaning. And as you probably know, the pellet cut geometry is a cylindrical type cut. This here just kind of gives you a good visual or pictorial of the more basic offering. The material strands exit the strand die in somewhat of a fashion of what you could consider like spaghetti strands. And this picture here is a representation of a standard water bath or water trough. The strands pass through this trough. Now there's adjustable equipment, rollers and such that you can extend the length through the entire bath, or you can allow the strands to exit the water with a shorter residence time. So there's some flexibility in terms of tempering. And then typically downstream of your water bath trough, you'll have what we call air knives. Some of them are vacuum style, some are positive airflow. That's again to kind of remove residual surface moisture from the strands as they enter the pelletizer. And then the pelletizer itself has a rotary top blade with, there's different sizes, different number of blades or teeth. And one challenge too with this type process is the length, the physical layout sometimes can be a challenge when strand pelletizing with if you have to have a larger, longer water bath trough. Here's kind of the same as what I demonstrated in terms of the water bath. This is kind of a typical setup. You'll see this is the strands have to be manually conveyed to the pelletizer, in this case via your operator. They'll typically have to manually grab the strands and walk them through and pass through the tank and then feed them into the pelletizer by hand. And so again, the water bath trough is for tempering. You have a heat exchanger to take heat off that process. Your heat exchanger normally will tie into either a central type cooling tower or water chiller type system. At the end of this bath, this is a vacuum air knife, so essentially the strands will pass through that. The vacuum pulls and tries to remove any surface moisture. And then, of course, the strands will feed into that chute there on the front side of that pelletizer, and then the rotary blades cut the material. Some other options here is a water slide unit with a dryer. So in this case, you have strands that will slide along this water slide. You have sprayer systems that'll help temper. Many times this unit can be a little shorter because you have the supplementary dryer unit where the pellets fall into a water system and are conveyed to the dryer unit for additional cooling and tempering. Another option is like a vacuum belt type system. Again, you start with a water slide, and then there's a transition to a vacuum belt. So water drains back into a recovery unit. And again, is equipped with heat exchanger to take heat off that process. And again, the principle's all the same. In terms of the infeed, it's just the different methods of tempering, whether it's a water trough with pass-through or sprayer systems, vacuum belt system. I didn't really have a good picture for this one, but another option if you're dealing with polymers that need to be non-water contact, these could be like degradable, like polyvinyl alcohol, or some of your starch-based. Instead of water, essentially you replace it with air. So again, the concept's similar. The strands convey along a conveyor, but you have air cooling instead of water cooling. The air is positive flow typically and can be either chilled or ambient flow. And again, just like all the other setups, the strands convey into the infeed rolls. A typical strand die assembly here. This is probably recognizable from many if you do deal with these, but you'll have the die adapter on the back side of that die, a rear adaptation to an 8-0. In some cases, you may have a recessed section where you can put a breaker plate with screen pack. Then you have the die, what's called the die body or the manifold heater assembly, then a bolt-on die plate on the very front side of that die body. There's different mounting support options, whether you do a hinge style or swivel or even a portable top frame. This here will kind of show you as part of that die assembly. You can see the die manifold in the upper left here. Typical top design. On the bottom left, geometry is an overview of kind of the internal bore, the typical design you'll see in a strand die, which is kind of mimics that of a film die to a certain extent with as like a fishtail or coat hanger design. On the right side, the drawings here, the die plate, this is what bolts onto the die manifold. And you can see the back side of the holes and then the front side. There's you can stagger these holes or single row. You can have double row, variable sizes. A lot of that's dependent upon your throughput and what size pellet cut you're targeting in terms of the diameter. This here kind of gives you a side view just to understand some of that internal geometry on that die plate. You typically have a lead-in angle and then what's called a linear land run. The main thing here is to understand that you do not want too steep of an angle. You don't want to force that melt to make a sharp transition leading into that linear land. It can cause some turbulent flow and some unstable flow exiting that die. So typically 60 degrees is recommended, no greater than that in terms of that lead-in angle. Now, strand dies can be a challenge. Really, this is kind of material dependent and product diversity dependent. In an ideal world, if you were set up on one single formulation, you can design that die typically that's more fitting to that particular application. Where the challenges take place is when you have a very diverse product portfolio, which is many times the case for compounders when they're running variable type polymers, variable type loadings, whether you're low loading or very high loading. And so it can create a lot of challenges with one single die body design. But just to kind of list here some challenges, obviously your throughput. Most die designers, when they design these extrusion dies, they're going to want to know throughput, melt density, melt viscosity, melt temperature to understand the flow and requirements on sizing. But when you run a diverse product mix, it's not uncommon to see a variation in extrusion rate, different product formulations. Some may be feed limited. You may not be able to run them as high a rates if you have a feed limited component. Of course, your specific gravity alone in many of your products can be quite variable on throughput in terms of pounds per hour. If you have high loadings of higher density type components can create higher specific gravity and such. Thermal gradients, and we'll look at this a little more detail, variable viscosity, material flow. Some polymers do have a greater change in viscosity over a small temperature range. When we talk about thermal control in terms of heating that die body, a lot of times it's a challenge depending on the type of heating. You can see some flow stagnation. Pressure differential is another one that is very common to see across that die plate. Of course, in some aspects, your hygroscopic type polymers, if they're processed undried with too much moisture present, you can experience some challenges with the strands separating and dropping. Some of your rigid application, particularly like glass fiber, depending on the loading of that fiber, many times when those strands enter that water, there's a quenching and they become very rigid and fragile in some aspects. Whereas between the die exit and the water bath, they're still kind of soft and elastic. So you can see some challenges. Sometimes there's separation if there's any surging in the process and such. And then, of course, die drool and fiber shedding at the exit of die. This is fairly common to see, a lot of times material dependent. So to understand a little bit on the material at the end of the machine, when it leaves the extruder, what's common is on any extruder, when you have a resistance due to a breaker plate, screen packs, die restriction, you'll see a backup length. And as that material backs up on the end of the machine on the shafts, it forces that melt to bypass the flights, the tip flights, and it forces them over the conveying, and you get additional shearing. And you can see here kind of on the bottom section to show that clearance. That's where your maximum shear peak is occurring, as in the very small clearance between the tip of the flights and the barrel housing. So what happens is when that material leaves that machine, there is some temperature differential, thermal gradients within the melt. And so as that material enters the die, it leaves the machine and goes into the die, it converts to pressure flow. And so there can be, with the existence of thermal gradients can cause some variable flow in terms of the viscosity. One thing you can do to kind of help mitigate this, whether you need to really do any melt filtration or not, is you can run with a standard breaker plate And what this does is this forces the melt when it's leaving the shafts, it's spinning and wrapping itself. You force that melt through that breaker plate and you can redistribute those thermal gradients. You're forcing the melt to pass through the very small holes of that breaker plate, and it will kind of homogenize those thermal gradients to kind of reduce that variation in temperature and viscosity. Another challenge with a lot of times in the strand, that strand manifold or the body is, with the fact when you think of edge flow versus center flow or internal flow, there's tendency to see some stagnation on the edge. That's because of the contact. You have an additional contact of that material with the top of the bore, the bottom, and the edge versus your center flow typically contacts your top and bottom portion of that internal bore. So you can see some slight differences in thermal conductivity from the barrel heating and such. So you can see a little bit of non-uniform flow. It's not uncommon to see some strands tend to swirl or have an erratic type flow on the outer holes. When we look at different plate heater or cartridge heater designs, there's good and bad to these. The key difference in the plate heaters versus the cartridge, the plate heaters are a lot more user friendly for maintenance in terms of replacing or installing. They bolt on, so they can easily be removed and replaced when they burn out. Whereas the cartridge heaters are more challenging to remove, depending on how long they've been in there. When the heating and cooling of those, the metal tends to oxidize, and they really can get stuck inside that bore. So they're not always easy to remove. Sometimes they have to be drilled out, but the key differences here is you get a little more internal heating with the cartridge heater. It's closer to your material flow path in the internal bore. So whereas the plate heaters are more kind of heating from outside in, so you're more externally heating. And we talked about a little bit on the materials processed. Um, your extrusion rates, if they vary on that machine, you may see variable flow on that strand die. And again, a lot of times this can be material dependent, depending on your components you're feeding. In some aspects, if you have no trouble feeding all your components, and you can run that machine at higher rates, whereas some material feeds can be challenging. Talc is one that comes to mind. If you're higher loading of talcs, 25, 30% or higher, a lot of times talc, depending on particularly if it's like a micro grade, very fine particle, it has a tendency to fluidize. Fumed silica is another one. And so those a lot of times will limit your extrusion rate. Your hygroscopics like PET and nylons, if those are processed undried, a lot of times the moisture can be an issue for them to cause some poor exit flow and from that strand die. And as I mentioned, some polymers are more sensitive to temperature change. The E of E sub A, the energy of activation flow, is different for different polymers. So depending on in terms of your temperature change, the viscosity can change more rapidly, and so you may see some challenges with the flow through the die. It's pretty common to see this. This is again kind of material application dependent. Some materials have a tendency to have higher die swell. In general, it's typical to see a little more pressure in the center area of that die plate. So it's not uncommon to see, if you look closely across your die face and the diameter of those strands, it's not uncommon to see the diameter a little larger toward the center. A lot of that's due to that edge flow stagnation. The pressures is primarily it's typically higher in the center region. It's challenging to really have very even pressure distribution across that die plate. So what you'll see a lot of times, depending on how drastic or dramatic this gets, you may have a tendency to customers plug the outer holes, trying to redistribute that pressure or take away some of those smaller strands if they're not flowing well or they're very small. Um, However, one thing I always kind of caution people is to, when you do that, can create additional stagnation in the corners and the outer areas. So just be mindful of that. Any material stagnation that hangs around, it could be degraded and then break free as a contaminant. And when we talked about, I touched on this already a little bit just to kind of provide a little visual. A lot of times those hygroscopics, that are moisture sensitive, that will react with moisture. You get hydrolytic degradation. Moisture can also act as plasticizer in some cases, and so you kind of get what's called a weak melt strength of those dyes. They tend to fall out of that dye and drop straight down. There's not a lot of strength to them so in some cases they could separate and drop out of the trough onto the floor. I mentioned a little bit like glass-filled compounds. What happens is your melt is still soft between the dye and the water trough, whereas once hits the water is kind of quenching and embrittlement from the glass, and sometimes those, depending on the polymer, those strands can be quite fragile. So sometimes you might see a breakage or separation at that juncture. This is probably another topic that you'll see come up. It's not uncommon with respect to processing time to see what we call dye drool or dye buildup. It can be glass fiber shedding at the dye face. A lot of this is it's what's really kind of a result of residual stress and the cooling. Once it leaves that dye and enters the air, and there's some cooling, there's relaxation of the polymer chains, thermal contraction, and some of this is just simply delamination of lower molecular weight species in the polymer. Could be shedding of glass fibers. Just note over time, if this buildup is significant enough and sits against that dye plate, it can be heated long enough that it starts discoloring, eventually can break off and be carried in toward the pelletizer and become a contamination. Just to kind of give a brief overview, I won't go into a lot of detail, but just to kind of give you a visual, if you're not familiar with kind of the standard design of these pelletizer units, but you'll have an upper feed roll and a lower feed roll. There's a doctor blade that transitions from feed rolls to your bed knife. A bed knife is what the rotor cuts against. It's the shear point to cut these pellets. And essentially, when you start this pelletizer unit, there's usually a position where you'll activate the upper feed roll. It'll lower into an operating position, and the strands are essentially sandwiched between the two rollers. The rollers control the strands. The idea is to feed the strands at 90 degrees to the rotary blade, so you want them to feed directly straight in. And we'll touch on some points later about when you start to experience wear. And essentially, of course, the rotor cuts the pellet geometry into a cylindrical. Again, that rotary cutter can be, different number of teeth, different widths, depending on your needs in terms of number of strands, your throughput rate. And overall, the pelletizer design, you have lab production scale size pelletizers. You can do single or dual drive. The single drive option basically just means when you adjust the pelletizer speed for the rotor, the in-feed rolls adjust at the same rate. So they're not independent. The dual drive gives you an independent control on the rotational speed, so you can change the speed of the rotary cutter independent of your in-feed roll, so you can adjust for pellet cut size. There's quick clean options to just for easier access to the cutting chamber, so when you're doing changeover cleanings, being able to remove any residual pellets or material within that chamber and that housing. The standard rotor usually is a stellite, but there are options on increased wear type options with like carbide coating for when you are cutting these more abrasive type components like glass filled. And then there's other options on even micro cutting, standard cut, or even long fiber type cutting options. So there's a lot. Your OEM can provide a lot of different options for you. So when we look at like pellet quality and common issues, you have angled cut pellets, there's tails, there's shards or fragmented. We'll see variable size pellets, double pellets, zipper, chain type. We'll go through these. In a perfect world, this is what the pellet should look like. You want free of imperfections, uniform size, shape, clean cross-sectional cuts. That's not always the case, of course. And so when we look at angled cut pellets, this typically, it could be different reasons. Your upper feed row could be worn, and so you don't achieve great control of the strand in feed. So there's a little bit of migration or wiggle room where that strand's wanting to shift one direction, left or right. And so then you end up, it goes in at a different angle to that cutting chamber, and then you get, of course, the angled cuts. And so it could be worn upper feed row. It could be possibly even just lack of proper alignment. When you move these pelletizer units are portable. They're typically mounted on wheels or casters. And so you have to align that with your strand in line with from the die exit through the bath or your slide into that feed roll. So just general alignment could be a gap issue between the bed knife and the rotor. So just some typical solutions is definitely check the wear of the upper feed roll. Another one is pressure. That upper feed roll has air pressure supplied on it. And so you want to ensure you have enough pressure that you're getting sufficient gripping or sandwiching of the strands as it infeeds into the pelletizer. And then evaluate your alignment, check your gap on your bed knife. And then the pellets with tails, this could be either, again, it could be a gap issue, could be worn rotor blades. Your blades may not be sharp enough to get a real clean pass-through cut. Material could be a little too warm. So again, check your gap. You want to make sure your wear condition of your rotor and bed knife. And then if it is a tempering issue, you can increase your residence time of strands in the water or cool the water temperature more if you have that capability. Shards or fragmented pellets. A lot of times the fragmented pellets are typically can be many times your tempering of the strands. It could be too cold, so instead of clean, it tends to fracture or basically kind of when on the impact of the rotary blades can cause fragmentation. Or it could be worn doctor blade or bed knife as well. So again, check the wear, reduce the residence time of strands in the water bath, and see if you improve your cuts in that sense. Variable size pellet cuts. Again, this can be related to your die swell, as we talked about earlier on the pressure differential across the die plate. Worn die plate could be as well an issue. Maybe some holes are a little larger just due to long-term wear. Could be intermittent process surge of an extruder. So if your extruder is surging, you'll typically see the pressure, the head pressure vary. And so when there's a surge in higher pressure, you'll tend to see the the strands kind of grow in terms of diameter. You'll increase in die swell at the exit, whereas when the pressure cycles lower, you'll tend to see the die swell reduce. So it could be variation due to that. Again, you want to check die plate wear condition, maybe check material dosing if you do see some swings in your pressure. And then, as we've touched on earlier in the presentation on plugging die hose, if all else fails, in many cases it can plug die hose to help try to offset any pressure differential. Another thing that's common too after the pelletizer unit is many people will use a classifier, and so you can screen off if the pellets are significantly different in sizes. You can use a screen classifier that will allow pass through of small cuts or fines or shards and so forth. Double pellets. This is, again, could be an upper feed roll issue. You're not getting good control of the strands. They're tending to migrate and possibly touch one another, making contact. So they're going in quite warm and they can stick to one another. So you can see double side by side, what we call pellets. Lack of proper alignment could be lack of control of your strand separation upstream. So upstream of your pelletizer, the very front, just prior to entry in the infeed rolls, there's often a equipment piece there that has basically separation to allow physical, so you can kind of put these strands and separate them. They're basically like it doesn't roll, but it essentially looks like a cylindrical piece that's slotted. So again, you might want to check, make sure you're getting good control of strand separation. As mentioned before, you want to check that, make sure upper feed roll, ensure proper pressure on that upper feed roll, check the overall alignment again, and then make sure your strands are properly separated prior to infeed. Now, zipper or chain type cuts, this is most common. The material's too hot. Many times that material tends to smear as that rotary blades are coming around, so you don't get a good clean pass through. Could be rotor blades wear as well, but again, you want to check just to make sure, rule that out, any wear condition if it's very dull rotor blades, or increase your residence time of your strands in the water, or cooler water temperature, so to improve that cooling of those strands. So when we talk about factors in terms of strands separating, we touched on this a little bit. I talked about the quenching. We talked about hygroscopics, but just some overall tips. If you're seeing a continuous or very quite frequent dropping of strands, just some tips and ideas from what I've seen. Again, if it's, it could be fragile strands once they're cooled. If you're getting surging in that extruder, could be because what happens when the extruder surges a little bit, you'll see those strands tend to fall back, or they'll kind of drop, and your pelletizer, of course, is constantly pulling. So it's almost like a tug of war match between the extruder. So you want consistent linear speed of your strands toward the pelletizer, but if there's any surging and such, can cause a little bit of pull against one another. And then if your strands are fragile, they're brittle in one aspect in the water trough, but they may be still soft and elastic between the die and the water, then you can see a separation at that juncture. Again, if you're dealing with what I consider excessive extruder surge, this can be a constant issue that you're always seeing. Again, that kind of that tug of war match between that pelletizer. You can see the pulling. It just literally separates the strands. Inconsistent die flow. Again, we talked about a little bit in terms of your die flow. You want good uniform flow through the die as much as possible. So it could be variation in temperature, whether you're not tempering controlling the temperature in the internal bore. Could be variable viscosity. Due to thermal gradients, you may not have sufficient heating of the material. Again, this a lot of times is material dependent, because some polymers, again, if their viscosity can change, particularly your semi-crystalline type polymers as well, they have a sharper melting temperature. So in terms of really controlling that temperature, some will flow better than others from the die, where some are a lot more sensitive to any lack of proper thermal control. Also, another thing to consider is your vacuum. If you are working with an application that has a higher volatile content, or you're really trying to remove a lot of volatiles, sometimes if you lose the vacuum, you can experience strands dropping and may not realize that the vacuum's been fouled and is not operating properly. So that essentially now those volatiles are kind of being entrained more into your strands. Again, we've touched on this a little bit. The hygroscopic polymers, again, with too much moisture being processed, a lot of times they're very delicate. They tend to droop when they exit the die. They can be also problematic in terms of separating and dropping. Another tip, or just to ensure any material buildup with respect to time, if you've been processing long term, any stagnation behind that die plate within that manifold bore, if there's material that tends to build up and hang around, it can cause some poor die flow issues. So you may have to shut down, unbolt that die plate, take a look at it, make sure there's not a lot of residual buildup of material that's constricting flow or interfering the die flow. And with that, that concludes it. I appreciate your participation, and I'll now turn it back over to Christian.
Thank you, Darren. And to everyone who joined us, a recording of this webinar will be available on 1cpm.com within the next week or two, where you can also find all of our previous editions as well. If you have any questions, please feel free to contact us at extrusion.sales@cpm.net. Thank you.